Okay, so 1.3 is all about continuity and behavior, and they do talk about limits, although we're not going to quite cover limits completely. So I'm going to start by giving you the definition of a continuous graph. You guys writing?
I'm trying. I'm trying to talk. I'm trying to get to a place where. You know what, Alan? You're going to.
Okay, so a continuous function is a function that has no breaks, no holes, no jumping. Okay, the bottom line is that you have the ability to trace the function without ever having to lift your pencil. Okay, so if you can draw it without having to lift your pencil, then it is completely continuous. Okay, so let's do some examples of a continuous function. Can somebody give me an example of one that is continuous?
A problem.
A problem.
A line.
Yes. A line?
Alan's going to give you an equation.
Y equals X. Ditto. Okay. Can somebody think of one that's not?
A piecewise function.
A piecewise function. Very good. So something that might like be something that went like this and then all of a sudden jumped and went like that. Okay. Piecewise functions are often not continuous. Something that's like 1 over x. 1 over x looks like this. Kind of has an hourglass effect, perhaps. Okay, where there's vertical asymptotes. Okay, you might have a function that looks like a straight line, but actually has a hole in there. Okay, so one thing that I want you to understand on the calculator is if you graph a function that has a hole in it, do you think you can see it? Yeah. You cannot see holes on a calculator, okay? Because the calculator has little pixels and it can't say, oh, I'm just going to only fill in part of the pixel. So it doesn't show up on a calculator, okay? So be aware that holes exist and you can't see them, okay? All right, so basically what's going to happen here is they're going to give you some functions and say, find the points of discontinuity. Okay, so before we go any further, I need to tell you and clarify there are 2 types of discontinuity. Okay, there is removable discontinuity. Oh my gosh. I'm just going to abbreviate that. Okay, so a removable discontinuity is when you see a hole. Okay, so the idea is if I took the hole out, it would still look continuous. That's how I remember. Okay, versus non-removable. Okay, so in non-removable, what's that? Hole? Yeah, that's what a hole, yeah. Like if I ask you what kind of discontinuity it is?
What? No, that's
Like that's the definition? Yeah. Hole, when you have a hole. Okay, so non-removable is if you have vertical asymptotes.
What's an asymptote?
An asymptote is like an invisible line that the function gets infinitely close to but never reaches. Or if you have a physical jump in the graph, okay? So non-removable are super obvious because you really see the jump. There's like steps going on. Vertical asymptote or a jump. Okay, so let's do some examples. Okay, so I'm going to start with a piecewise function. So let's say one piece is 1 over x when x is less than 0, and the other piece is just x if x is greater than or equal to 0. Okay, so the way that you find points of discontinuity is any value that makes the denominator 0. Okay, so of the two pieces, let's start with the top piece. Is there any value that would make the denominator 0? 0. Okay, so that means that there's a vertical asymptote at 0. Okay, so there's a vertical asymptote at 0. How do I know that? Because the denominator is 0. Okay, so I can say there's a vertical asymptote at x equals 0. Okay, so anything that makes the denominator 0 causes a vertical asymptote. Okay, so graphically, and you could graph this in your calculator if you wanted to. Okay, 1 over x, remember 1 over x, I showed this to you up above, right there, that green one on the far right. Okay, so if I was going to draw that, but for only values of x being less than 0, what would I draw? Just that bottom left side, right? Okay, so the left-hand side would be from here to here. Okay, and then when x is greater than 0, I now have the function of x. So what does the function of x look like? On its own, if I just say graph x, y equals x, what does it look like? Straight line, right? A slope of 1 goes through the origin with a slope of 1. Okay, is that function continuous on its own? Yes. Okay, there's no jumping, there's no holes, there's no denominator that would make that 0. It would be continuous on its own. Okay, so what I'm going to do is I'm going to draw it, but only when x is greater than 0. So where am I going to start? At 0. Yeah, because if I plug 0 in, it would be at 0, 0. So I include this value, and then I have my line that goes up. Yep, there is an asymptote at 0. Okay, so there is, but it's only on the left-hand side. Okay, so we're going to talk about that discontinuity. What do you see happening at the value of 0? Is it a hole? Is it an asymptote? Is it a jump? This one's kind of a weird one because it's kind of like a jumpy asymptote. It's a jumpy asymptote because the right-hand side actually exists at that asymptote. Okay, so what kind of discontinuity do I have? Is it a removable or is it a non-removable? It is absolutely a non-removable. Okay, so it's a jumpy asymptote. Either way, a non-removable. Okay, so you'd have a non-removable discontinuity at x equals 0. That's supposed to be an at. There we go. Okay, so that's the kind of answer I'm going to be looking for. I'm going to be looking for, is it removable or non-removable, and what x values? Yes, that's an at sign. I had a little trouble drawing it. Okay, let's do another one. Let's make sure we're super clear on all this. Whoa. Okay, so let's say we have a function 1 over x minus 1. Okay, so number 1, do I have any points of discontinuity? Okay, so first of all, what causes discontinuity in a function? What is the one thing you can't divide or do? Whoops, I totally almost said the answer. Divide by 0, right? Okay, so any x value that would make the denominator 0 causes points of discontinuity. Okay, so what's the value that causes that discontinuity? X equals 1. Okay, so now you have to decide, is it a vertical asymptote or is it a hole? Okay, so how do we decide if it's a hole? Let's go over what a hole looks like, by the way. Let's do a side note. I'm going to give you this crazy function real fast. This is my side note. So we have x plus 3, x minus 2 over x minus 5, and x plus 3. Okay, so if you look at this, there are 2 points of discontinuity. What are the 2 points of discontinuity? There's 5 and negative 3. 5 and negative 3. Everybody looking at the denominator, what values make those quantities 0? Okay, now, if you look at the top, what do you notice with the bottom?
There's 3
on one of the quantities. Yeah, so these quantities that cancel, when a quantity cancels out, that creates a hole. Okay, so that means there would be a hole, which is what kind of discontinuity, by the way? Removable, at x equals negative 3. If it does not cancel out, that's a vertical asymptote. So what's positive 5 going to be? What kind of discontinuity? Non-removable. Nice. Non-removable at x equals 5. Maybe I should have done that one first. Looking at the denominator, what value makes x minus 5 0?
Is there any equation that is just removable?
Oh yeah. So like if I had what if I had x and x plus 5 over x? Okay, so the x's would cancel. There is a hole or a removable discontinuity at what x value? At 0, right? So this would be a removable at x equals 0. Okay, so what was my number 2 example? What kind of discontinuity? No, it's impossible to be both. You can't have both. It's either a hole or an asymptote. It's not both. What's that?
That first example, or the third example.
Okay, I see what you're saying. Okay, so when I say both, I was thinking like at the same x value. So you can't, like, if the discontinuity occurs at 2, you can't have an asymptote and a hole at 2, but you can have different kinds of discontinuity throughout the function. That's what I mean by you can't have both. So like on question number 2, there's only 1 point of discontinuity. Which kind is it? It's what? It's non-removable, right? It doesn't cancel. It's a non-removable. It's a vertical asymptote. This is a non-removable.
Wait, so that example with the removable and the non-removable, those 2 x values can't exist on the same graph. Is that what you're saying?
No, I'm saying like at the x value of negative 3, if I was only talking about x being negative 3, you could not have an asymptote and a hole. It's got to be one or the other. At the same x value. Yeah, you could have 100 different kinds of discontinuity throughout one graph. You'd never see that, but it's possible. Actually, there's lots of different ways. Let's not go there yet. But at a single x value, you can only have one kind. Keep going? Yes, more? Yes? Still not getting. Okay, let's do number 3. Let's keep doing this stuff. Let's do Okay, so what about this one? How many kinds of discontinuity do I have? Or how many points? So 2 places where it's not continuous. 2 places. What are the 2 places?
X minus 3.
Okay, at x minus 3, so x being 3. And then the other one is at 8. So it's at 3 and 8. Okay, so I have to decide, is 3 a removable or a non-removable? Why? There you go. Okay, because they could cancel. So we have a removable at x equals 3. Okay, so that means 8 has got to be what? Non-removable. X equals 8. Nice. Okay, let's dabble a little bit more with the piecewise function. Because they're going to throw that at you more often than not. Okay, I'm going to do this one completely algebraically. I'm not even going to think about the graph. I'm just going to look at my 2 pieces. Okay, so for starters, if I look at just the top piece, the 3x minus 2, does that have any points of discontinuity? (3x minus 2). Is that continuous? Not continuous. It is continuous. Very good, okay? So 3x minus 2 would just be a straight line. We're not dividing by x ever, so that one is completely continuous. What about the bottom piece? 2 minus x. Continuous. Okay, so both pieces are continuous. So now, since I'm dealing with 2 pieces, what I have to decide is, do the 2 pieces come together and meet and create a continuous function, or is there a jump?
How do you know they're used to start with?
Because neither of them have an x in the denominator. That's the only way you can have it. Okay, so how am I going to decide if they come together when they're supposed to join? Okay, what is the value that we're looking at? What x value are we trying to figure out if it's continuous at?
Hey, I was right.
-3. Okay, where the function stops and where the other one starts.
And it has to be.
Okay.
It has to be less than. Right.
No. We're just going to plug -3 into both of them and see if they meet at the same place. They have the same y value. Okay? So if I plug -3 into the x value of the top piece, I would get -9 minus 2, which is -11. If I plug -3 into the bottom one, I get 5. Do they come together at the same place? 2 plus 3 minus a negative. Okay, so they do not come together. There is a jump. So how do I say what is my point of discontinuity? What kind of discontinuity do we have? Non-removable at what x value? What x value? -3.
So what if those aren't the same number? What if one of them -3 is like 7?
Okay, in that scenario, you won't see that, by the way. But, I mean, it's always, I guess anything is possible, right? So if they were not the same number, then there would be a spot in between the numbers. So if it was like from -3 to 7, there would be a giant gap between this function existing. So there would be like a whole set of non-existent values. So there would be a jump. I don't know how you would say that continuous y, because there's a jump of x values. I've never seen that before.
If you plug -3 in both those, they both equal -11.
Correct. No, it would be continuous. It'd be continuous because the 2 pieces would come together and therefore become continuous.
Gotcha.
Yes.
Do that same thing with both always be the same direction. So like say the top one was x is less than -3.
Okay, so in that scenario, you would have a line over a line.
Yeah.
Is that a function? Does that pass the vertical line test? So technically, it would not be a function. So they're only going to give you pieces that are actually functions.
So it's never going to be removed. Like if there's two different equations, x greater than.
The only way it could be removable is if they did come together at the same place, but the inequality sign was greater than and less than, and never actually included the value of 3. They'll never do that to you either, because that would be super like detail. Like I've never seen them do that either. But that's the only way it could happen. Is if they look continuous, but the number they're looking at is a whole. You see what I'm saying? All right, so are we good on discontinuities?
And go.
What's that?
Yeah.
Good for now? All right, so let's do some calculator work here. So we are going to next find zeros using calculator. Okay, so first of all, if I say finding zeros, what are we looking for? The x-intercepts. Okay, so I'm going to show you how to do this on the calculator. Okay, so algebraically, you would just set the function equal to 0 and solve it. Well, that isn't always possible. So sometimes you have to use a calculator. So this would be an instance where you have to use the calculator in order to find the zeros. All right, so I'm going to start by graphing it. So we're going to throw it into the y1. So we've got x to the third minus x squared minus 3. Okay, and remember when you're graphing for the first time, you don't know what the last person's window was, so always hit a zoom 6 right away. Zoom 6, so we got a standard 10 by 10. Okay, so again, we're looking for where this function is crossing the x-axis. Notice that we're given a defined interval between -2 and 4. Okay, so if I look at this and say, oh, it's crossing way over at 10, do I need to find that 0? No, I'm only looking between the x values of -2 and 4. Okay, so I can clearly see it crosses at least once. Well, okay, just only once. How do I find a 0 using the calculator? What buttons do I push?
Second trace.
You hit second trace, good. And we are finding a 0, so we're going to do number 2. Okay, and the complicated part is that it first asks this question. It says, go to the left of that spot. Okay, so you're using your cursor. Right now, I am currently left of the 0. Okay, so I'm going to hit enter. Okay, then it says go to the right, which means go to the other side of the x-axis until you're to the right of it. So I'm going to push the right arrow until I'm to the right of it, which is really slow on this. There we go. Okay, and then it asks me for a guess. The guess, as long as my 2 arrows are pointing at each other, I'm fine. I'm just going to hit enter. Okay, and it's going to pop out the x value where it crosses. Okay, so what would you say? We're going to round to 3 decimal places on this. 1.864. So I'd say x is equal to 1.6. What was it again? I lost it. 864. Oops. 864. Did you round up?
No.
Oh. Should I do one more of those? One more? Okay. Number 2. Ooh, let's do a square root, because they like square roots. We'll do the square root of x cubed minus 1. No, plus 1, sorry, minus 5. And our interval is going to be between 0 and 5. Alright, so we type it in. Square root of x cubed plus 1. And then make sure you go outside of the radical to do the minus 5. Okay, so remember we're just looking between 0 and 5 on this one. Okay, so how many do you see? Just one? Yeah? Does everybody have the same graph that I do? Oh, well maybe you could work together. You don't have the same function that I do? Now you do? Because it's possible I typed it in wrong. You never know. You did? Okay. Whew. Okay, so now what do I do to find the 0? Second, trace. I choose number 2. I'm going to go to the left. So right now I am on the left of it. I'm going to hit enter. Then I'm going to go to the right, which is going to go to the other side of the x-axis. Make sure that the 2 arrows are pointing at each other. And since they are, I'm going to hit enter for the guess, and it should pop out my answer. So I see 2.884. Did anybody else get that?
Yeah.
Okay, good. So we say x is equal to 2.884. Done and done. And done. Awesome?
So awesome.
Okay, we got one more thing.
How do we know if we need to use that?
It'll tell you. This thing is end behavior. Okay, so the end behavior is the farmost ends of your function. Okay, so for example, if I was a parabola and I was going to make my body become a parabola, I'm kind of looking at my hands, right? I've got a right hand and a left hand. Okay, so I'm looking at where these hands are going. So if I have a parabola, where are both my hands going? Up to where?
Yes.
To infinity. Okay, so you can be going up to infinity. You could be a John Travolta. And so I have a right hand that's going up to infinity and a left hand that's going down to infinity. Okay, so that's what we're describing. Okay, so we're going to have an answer for your left hand and an answer for your right hand. Okay, so here's our example. 2x squared plus 4x minus 5. Okay, and I anticipate that you should be able to do this without using a calculator. Okay, what does this look like? How did you know it's a parabola? X squared. Very plain, very simple. I am looking at the leading coefficient. It is a positive x squared. It's a parabola. So what are both of my hands doing? Going to infinity. So I'm just going to write right end and left end are both going to infinity. Okay. Yeah. So they'll make it a slightly more complicated. Well, I don't know if this is much more complicated, but here is one that's more complicated. Let's say I have 2x to the 5th plus 4x. What does that look like?
would be
What do you mean the squiggly line? How squiggly of a line? Okay, well, what does this basically look like?
Like this.
Okay, basically it looks like a John Travolta. Okay, so we know that it looks like a John Travolta because the exponent is odd. Okay, anything cubed to the 5th, to the 7th, to the 9th, to the 211th would look like a John Travolta. Okay, and the same goes for any even exponent. If I have an even exponent, I would have some kind of parabolic function. Okay, it's possible if I have like 2x to the 10th that I could have a parabola that does some crazy wiggling in between and then goes back up. But in the end, it's still going to look parabolic. Okay, so I would say for this one, because I have a positive John Travolta, the right hand is up, left hand is down. I would say right end goes to positive infinity, left end goes to negative infinity. Okay? Everybody okay with all this? So your assignment's on page 30, and you have 2 through 40 evens.